Assalamualaikum and hi everyone. So today we are going to learn a new chapter which is integration. In previous chapter we have already learned about differentiation and its application. So we know a lot about differentiation now. And today we are going to learn a new chapter that are very much relate to differentiation, which are called as integration. In this video we are going to focus about the algebra of definite and indefinite integrals. At the end of this lesson, you should be able to calculate the indefinite and definite integrals functions. Let's go for the introduction. Integration is simply known as the inverse process of differentiation. Now, let us recall back about the differentiation process. Let's say we have a function of fx and the lowercase of fx is the derivative of the capital of fx. So we know that in order to get lowercase of fx here, we have to differentiate the capital of fx. Then we get its derivative. Now, let's go backward process. A purpose of doing so is that we need to return back to the original functions. So we have to do with the integration process for the lowercase of fx to get back the original function of capital Fx. So this is called as the entire derivative. So what is entire derivative? Well, that's a function for which if we take the derivative of a function, then we will get back to its original function. So in this case, the capital of fx is the entire derivative of the lowercase of fx. For instance, suppose the capital of fx is equal to x to the power of 5 plus 2x plus c is the entire derivative of fx. So we know that the lowercase of fx we will get as 5x to the power of 4 plus 2. So before we are going further or deeper on the integration process, let us learn and study about the integral notation and symbol. This symbol is known as the integral sign. At the upper of this integral sign, there is b, which is also known as the upper limit of integration. And at the bottom there is a, also called as a lower limit of integration. Inside the integral, there is a function of fx. The function is called as integrand. X is the variable of integration here. And the whole thing here can be read as the integral of f from a to b. When you find the value of the integral, you have evaluated the integral. Integrals can be divided by two, which are definite integral and indefinite integrals. Definite integrals evaluating the entire derivative over a specific number or interval. But sometimes we will be looking at the integrals with no limit of interval. This is called as indefinite integrals. The main difference here is that definite integrals give numbers, but the indefinite integrals give functions. Let's focus with the indefinite integrals first. If we differentiate the capital Fx with respect to x, we will get the lower case of Fx. Then, if we differentiate the capital of Fx plus c, then we can separate the differentiation process like this. Then we get the lower case of Fx plus 0. So, the integral of lowercase fx dx is equal to the capital Fx plus c. The arbitrary constant c is called the constant of integrations. So, whenever we have the entire derivative function, we must put c at the end of the result. So, fx plus c is called the indefinite integral. Now, let's learn about the properties of the indefinite integral. The first properties is that integral k multiplied by fx dx is equal to k multiplied by the integrals of integrands. Meaning that we can always put the k constant outside the integral. The second properties is similar like the first properties. We have to put the negative sign outside of the integrals. And then the last properties is that any addition or subtraction, we can actually separate it like this. Now let's move to the table of indefinite integrals. So as you can see here in the table, there are so many properties of indefinite integrals. So let's just discuss some of it. So the first properties here is that integral k dx means that if we integrate any constant number or value, it will always equal to kx plus c. The second properties there is the integrals of x to the power of n dx. So for these integrals, we have to plus 1 at the power at x to the power of n plus 1, and then at the denominator we have to put all the power that we have added and plus c. Let's go for example 1. The integral of x cubed plus 3x minus 3 dx. In this case, we can integrate it separately. So let's do this one by one. The integral of x cubed, we will get x the power of 3 plus 1 over 3 plus 1. So we will get x to the power of 4 over 4. And then the second integral we get 3x squared over 2. And then integrals negative 3 dx will get negative 3x. And then lastly, don't forget to plus c. Example 1b, the integrals of 1 plus 5x, which is in bracket, multiplied by x cubed dx. So for this case, it is easier if we expand first the function. Okay, so now we will get x cubed plus 5x to the power of 4. And then now we can separately integrate it. So we get x to the power of 4 over 4 plus 5x to the power of 5 over 5. So we cancel out 5. We get x to the power of 5 and then plus c. Example 1c. The integrals of 1 plus square root of x over x to the power of 4 dx. In this case, actually we can separate it, the fraction. So we get 1 over x to the power of 4 plus square root of x over x to the power of 4. By law of indices, we can actually get x to the power of negative 4 and x to the power of negative 7 over 2 dx. Now we can integrate it now. So we get x to the power of negative 3 over negative 3, because negative 4 plus 1 we get negative 3, and then plus x to the power of negative 5 over 2 over negative 5 over 2, and then plus c. And then rearrange, so we get negative 1 over 3 x to the power of 3 minus 2 over 5 x to the power of 5 over 2 plus c. Example 1d, the integral of 5 over in bracket 3x plus 4 dx. So in the table of properties, we already know that we can put the constant outside. So we put 5 outside, multiply by the integral. So we get like this. And then refer back to the table of properties. We also know that the integrals of 1 over x dx is equal to ln x plus c. Okay, so it is same with this case, which we can integrate 1 over 3x plus 4. Now become 5 multiplied by ln 3x plus 4. So as you notice that we have another function inside ln, which is 3x plus 4. So we must differentiate 3x plus 4 at the denominator. And then don't forget to plus c. And after that, we get 5 ln 3x plus 4 over 3 plus c. Then rearrange, we get 5 over 3 ln 3x plus 4 plus c. Example 1e, the integrals of e to the power of 3x dx. If you get any exponential function, so you refer back to the table properties, you get integrals of e to the power of x dx, always get e to the power of x plus c. Okay, now we integrate it, we get e to the power of 3x. And then notice that there is 3x because there is a function there. So we have to differentiate at the denominator again. So we get d over dx 3x. Then forget to plus c also. And then we get e to the power of 3x over 3 plus c. Example 1f. Integrals of 3 sine 3x dx. Okay, first we put 3 as the constant outside. Then we get 3 integrals of sine 3x dx. So looking back at the table of properties, we know that the integral sin x dx is equal to negative cos x plus c. So now we will get 3 in bracket negative cos 3x, and then we have another function inside cos. We have to differentiate at the denominator for 3x, then plus c. Now we get negative 3 cos 3x over 3 plus c. Cancel out 3, we get negative cos 3x plus c. Example 2. If f prime x is equal to e to the power of 5x plus x, and if we substitute 0 inside the function of fx, we will get 3 over 5. Find fx. So we have f prime x is equal to e to the power of 5x plus x. So to get back to the original function, of course we have to do the integration process, which is integral of f prime x dx. We get fx. So we integrate it, we will get e to the power of 5x over 5 plus x squared over 2 plus c. And then after we get the function of fx, we substitute 0 and then equal it with 3 over 5 to solve the c value. And then substitute it, we get c is equal to 2 over 5. And then substitute c inside the original function of fx, so we get e to the power of 5x over 5 plus x squared over 2 plus 2 over 5. Let's move on to definite integrals. Definite integrals, we usually evaluate it over a specific number of interval. So the main difference between indefinite, usually the answer will give in function itself. But the definite integral, it will give the answer as in number or value. The definite integrals denoted by the integrals from a to b, which is the lower limit up to the upper limit. Fx is the integrand dx. Okay, after we integrate it, we have to put in bracket capital Fx. So close bracket. So now we have to put the lower limit and the upper limit at the right hand side of the bracket. So it looked like this. And then it also denoted as capital Fb minus capital Fa. Okay, let's look at the table of definite integrals. The first property said that the integrals for a single value, which is from a to a, fx dx is equal to 0. Which means for a single value, for a single vertical value here, vertical line, we get 0 because there is no area under a certain graph curve. So of course it's equal to 0. Okay, the second properties is that the integral of from b to a is equal to negative integral of from a to b. Which means if we change the upper to the lower limit upside down, it will become vice versa of sign. Okay, and then the third properties is that the integral of from a to b is equal to the integral from a to c plus the integral from c to b. Okay, to get clear for this, let's see for the example. Okay, let's say at this graph curve, we can see that the c is in between a and b. So we know that we can use these properties because all the value are inside the same function. Okay, the fourth property is any constant number can be put outside, so it pretty similar like the previous indefinite integral properties. And also at the fifth properties here, it's also the same properties like the indefinite. We can separate the addition and subtraction process. So now let's move on to another example. Example 3. Find the integrals of from 1 to 3 x in bracket 3x plus 7 dx. So we have to integrate like usual. So we get 3x cubed over 3 plus 7x squared over 2, and then put in bracket, put at the lower limit, which is 1, and the upper limit is 3. And then we have to substitute the upper limit first, which is 3, inside the function that we have integrate. and then minus with the lower limit of value, which is 1 inside the function. So we get 117 over 2 minus 9 over 2 is equal to 54. So we know that the definite integrals, we get the answer in the value or number. So let's move to example 4. Evaluate the integrals of from -1 up to 2 fx dx if fx is equal to e to the power of 3x if x less than 1, secant square 3x if x more or equal than 1. So for this case, for piecewise function, we know that we have two function here, which is e to the power of 3x and secant square 3x. So we can choose we can use the properties, the third properties, which is as shown here. So we get -1 up to 1 for the function of e to the power of 3x dx because the region is x less than 1. Okay, so another function which is secant square 3x. So we get the integral of from 1 to 2 because the region said that x must be greater or equal than 1. So here we use the properties, so we will get e to the power of 3x over 3 with the specific number of up limits plus tangent 3x over 3 from 1 up to 2. So substitute all and then we get the final answer 1/3 in bracket e to the power of 3 minus e to the power of -3 plus 1/3 in bracket tangent 6 minus tangent 3. Okay, example 4b. The integrals from 0 up to 1 fx dx. Okay, so we have to integrate first. We will get e to the power of 3x over 3 and then substitute the upper limit minus the lower limit, so we will get 1/3 in bracket e to the power of 3 minus 1. So that's all for chapter 4.1, indefinite and definite integrals. So let's check your comprehension.